Hey everybody. Today we're talking about bivariate distributions of continuous random variables. Here we're in a situation where we have two or more continuous random variables that potentially depend on one another. And those probabilities are going to be defined by a joint probability density function, a joint PDF. And this is going to work in much the same way as for distributions of a single random variable. A joint PDF, call it f of x comma y, has to satisfy two basic properties. First of all, it always has to be positive. Probabilities and probability densities can never be negative. And they have to integrate out to 1. So the integral over the entire real plane of f of x comma y dx dy has to be 1. And this is reflecting the basic probability idea that when you run a probability experiment, something has to happen. Probabilities are calculated by multiple integration, much in the same way as probabilities are calculated by regular integration for a single random variable. If you have some set of points, x comma y, call it D, like a region in the real plane, the probability that x and comma y is in D is given by the double integral over D of f of x comma y dA. The set of points x comma y where f is actually strictly greater than 0 is called the support of the distribution. So that's a definition that's directly in parallel to the definition for a single continuous random variable. Oftentimes we can compute double integrals one at a time, and that's called iteration of integrals, and it's permissible whenever the function f is continuous. Most simply, if you have a rectangular region given by x in the range a to b and y in the range c to d, you can do the double integral just by doing one integral followed by the other. And the order doesn't particularly matter for rectangular regions. So for instance, if you're integrating with respect to y first, you integrate from y equals c to y equals d of f of x comma y dy, and then you take that result and integrate it with respect to x from x equals a to x equals b. When you're doing that first integral, the one that I just said was with respect to y there, you're treating x as a constant. You're not considering it as a variable at all. So really you are just doing a single variable integration two different times with respect to one variable and then the other. Let's get into an example. That's where I think this all gets to be more clear. So I've got two random variables, x and y. They're continuous, and they have a joint PDF. F of x comma y is 1/16 x plus 3y. And this is going to be defined on the rectangular region x between 0 and 2 and y between 0 and 2. By the way, if you do out the double integral of f of x comma y over 0 comma 2 cross 0 comma 2, you will get 1, and you should check that on your own. I want to compute the probability of that x and y wind up in the rectangular region 0, 1 cross 1 comma 2. That is, x is between 0 and 1, and y is between 1 and 2. So I'm going to compute this double integral through iteration. First I'm going to integrate from y equals 1 to y equals 2. Then I'm going to integrate from x equals 0 to x equals 1. I could do that in either order. It's not going to matter since we have a rectangular region. First, I integrate with respect to y. So I'm treating x as constant, integrating with respect to y. The result is 1/16 y times x plus 3/2 y squared. I'm going to evaluate that from y equals 1 to y equals 2 to get x plus 9/2. I've factored out the 1/16 from the integral, by the way. And now I'm going to integrate that from x equals 0 to x equals 1. I get my antiderivative, I plug in 0 comma 1, and I get 5/16. Notice that the region that I just integrated over is 1/4 of the area of the region where the PDF is non-zero. It's 1/4 of the support by area. But it includes 5/16 of the probability. And that's because the joint PDF is larger for larger values of x and y. So probability is more concentrated in the upper right quarter of the support. Here's a picture that goes with that. I'm showing the probabilities for each of those 4 different corners. We computed the probability in the upper left-hand corner. You should do at least one or two of these others just for practice to make sure that you're getting the same values as me. Also notice that if you add up all 4 of these values, you do get 1. The total probability of something occurring in this probability experiment is 1 as always. Things get a little bit more difficult, interesting, when the region D is not just a rectangle. For instance, we might want to compute the probability that x comma y is in the triangular region that I'm showing here. In order to write this as an iterated integral, we need to come up with inequalities in x and y that fully describe this region. The way that we're going to do that is we are going to come up with first an inequality for one of the variables. For instance, we could say that x is between 0 and 2, and then come up with another set of inequalities for the other variable. Now, for that second variable, the limiting values of y can potentially depend on values of x. So, when x is between 0 and 2, as we've already decided it must be from our first set of inequalities, the shaded region lies above the line y equals 2 minus x and below the line y equals 2. I think it's helpful to draw in a rectangle just as you would as if you were setting up an integral for area between curves. Here, the top curve is y equals 2, the bottom curve is y equals 2 minus x. And so the region is defined by the inequality 2 minus x less than y less than 2. Okay, so overall we have these 2 inequalities that define the region, also x being between 0 and 2. So we're ready to set up our iterated integral. We put the variable that just has constant limits on the outside. So the outermost integral is going to be from x equals 0 to x equals 2. We put the other integral, the one that uses the variable that is relative to the other variable, we put that on the inside. So we go from y equals 2 minus x to y equals 2. And then, of course, the inside is just f of x comma y. Now we integrate. I'm not going to walk through this all step by step, but do notice that after you do the first integral, the things you're plugging in for y also involve x. So the single integral you're doing for x, for that second integration, is potentially a little bit harder. Now in general, you can use this technique whenever the region D can be represented as the region between two curves, y functions of x. So you've got a bottom curve and a top curve. You could use the same technique if D could be described as the region between two functions of y. So instead of a top curve and a bottom curve, you have a right curve and a left curve. And in that case, you're going to parameterize the region based on two y values that are just fixed numbers, y equals c and y equals d. And then your limits for x are going to be functions of y, the equations of the right curve and the left curve in terms of y. In that situation, you'll be integrating with respect to y first, and then with respect to x. In the last example, you can also describe it by bounding x between functions of y. And you should try that for practice. So I describe this region by bounding y in terms of functions of x. And you can check that you're doing that right by making sure that you get the same answer as that I got earlier, which was that probability should be 2/3.